Okay, so we want to predict how the graph of y equals 2 sine 1/2 x minus pi over 3 minus 1 is related to the graph of y equals sine of theta, or sine of x I should say perhaps. So working with x. So first things first, we're going to make some predictions in terms of what's happening with this graph. So if you compare those two graphs, what can you identify? What's happening? In terms of transformations, what's happened? Group? Pi over 3 units, right? But before we look at translations, what's the first thing that we look at? Yeah, stretches, expansion and compression. So is there a vertical expansion? Yeah, by 2. So we have a vertical expansion by 2. So what does that mean? It means in a sinusoidal graph, our amplitude of the graph is going to be 2. We have a horizontal horizontal expansion by 2 as well. What that means in sinusoidal function is that the period of the graph has changed. If it's been horizontally expanded by a factor of 2, we've gone from a period of 2 pi to a period of 4 pi. And we can also determine that by using our period formula. So period equals 2 pi divided by b, which is 2 pi divided by a half, which is 4 pi. Right, now just make a note of where we're getting these pieces of information from. This is representing our vertical expansion. This is representing our horizontal expansion by 2. Okay, next up we look at our translation. So pi over 3 units to the right. So we call that the phase shift. We have a phase shift of pi over 3 units right. And then lastly we have a translation of 1 unit down. So we call that vertical displacement. 1 unit down. Now we're going to learn how we can graph these transformed functions. So we're going to start off by taking a look at what our phase shift is. You'll notice that the phase shift is pi over 3 units. So eventually we're going to be moving our graph to the left pi over 3 units, either left or right, whichever direction our phase shift is in. So when I set up my scale, I'm going to set up my scale as factors of pi over 3. So that way moving the graph left or right is really easy, just 1 box over or 2 boxes over. If I set up my scale differently, then I'm going to have a hard time moving them left or right. The points are going to end up somewhere in the middle and it's going to be a messy graph. So based on this phase shift, I'm going to set up my scale in fractions of pi over 3. So what does that mean? That means I have to go up in increments of pi over 3. I want to maximize the space I use. I want to go from 0 to 4 pi. So let's say I went every 2 boxes is pi over 3. See if I can fit that in there. So pi over 3, 2 pi over 3, 3 pi over 3 will be pi, 4 pi over 3, 5 pi over 3, 6 pi over 3 will be 2 pi, 7 pi over 3, 8 pi over 3, 9 pi over 3 will be 3 pi, 10 pi over 3, 11 pi over 3, 12 pi over 3 will be 4 pi. Right, I'm going up in fractions of pi over 3. And if I want to label them, it'll be pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3, 7 pi over 3, 8 pi over 3, 9 pi over 3, 10 pi over 3, 11 pi over 3. Right? That's my scale factor, going up by pi over 3 each time. Okay, now that I've set up my scale, I'm going to start off with I can also graph the original function and work from that, but I'm going to skip that step. I'm going to go straight to the function by taking into account the amplitude and the period. I'm going to graph these together first, the amplitude and the period. Actually, let me do the original graph, just so you have an idea of what the original sine function looks like. So if you're graphing the original sine function from yesterday's lesson, you will know that sine starts at 0. It's got another x-intercept at pi and another x-intercept at 2 pi. Right? It's got another x-intercept at 3 pi and then 4 pi every pi units later. At pi over 2, at 90 degrees, sine of pi over 2 is 1. It's going to have a maximum value of 1. So at pi over 2, which is halfway between pi and 0, it'll have a maximum value of 1. And at 3 pi over 2, which is halfway between pi and 2 pi, I'll have a minimum value of negative 1. So I'll get this original graph. Okay, that's going to be the original graph sine of x or sine of theta. Similarly, it's periodic. It's going to continue on. It's got zeros at 3 pi and 4 pi. Halfway between those, at 5 pi over 2, it's going to have a maximum. And at 7 pi over 2, it's going to have a minimum. This is the original function, y equals sine of x. It looks a little different from what you saw yesterday because the scale has been changed a bit. Instead of going up by fractions of pi over 4, we're going up by fractions of pi over 3 or pi over 6 if you look at every single box. Are we okay with the general shape of that graph? Right, sine of theta. The key idea you want to remember is sine starts at 0, it's got another x-intercept at pi, another one at 2 pi. In between 0 and pi is the maximum, in between pi and 2 pi is the minimum. Because sine's got an amplitude of 1, 1 and negative 1. That's the general shape. Now we're going to graph the new amplitude and the new period all together. And this is the tricky part. This is what you want to pay close attention to. So our new sine function has an amplitude of 2 and it has a period of 4 pi, which means it's going to start at 0 and it's going to end at 4 pi. It's going to last a full 4 pi. Because we've stretched it horizontally by a factor of 2, we've pulled it out, it's going to be sort of a stretchier sine curve. So it starts at 0. So let me use the red color here so it's a bit more visible. Starts at 0. It's going to end at 4 pi. Normal sine function, this is where you need to remember the general shape of a sine function. A sine function will look like this. Starts here, ends here. In between the starting and the ending point is another intercept, the 0. Right? So using that concept, if it starts at 0, ends at 4 pi, at 2 pi it's going to have another x-intercept. In between the first and the second intercept, it's going to have its maximum. So if it's got a 0 at 0 and 2 pi, at what value is it going to have a maximum value? At what x value? Pi. And what's the maximum value going to be? 2, because the amplitude is 2. So at pi, it's going to have an amplitude of 2. And similarly, in between the second and the third intercept, between 2 pi and 4 pi, it's going to have a minimum value at negative 2. Right? So I end up with this new graph. This new red graph. This red graph, I'll label it, is now the graph of this portion of my transformation. Y equals 2 sine 1/2 x. Okay, that's what I've graphed. I've graphed the amplitude and I've graphed the new period. That's what I've graphed. The final thing I'm going to add, just like I did with transformations, is I'm going to go ahead and now add the translations, which is the vertical displacement and phase shift. I need to move this graph pi over 3 units to the right and 1 unit down. So I will use the color. Let's see here, what color can I use? Blue, red we've already used. Let me use black this time. I want to move that graph pi over 3 units to the right and 1 unit down. So I'm going to take each of my key points, I'm going to move them pi over 3 to the right and then 1 unit down. So 0, 0 is going to end up at pi over 3 negative 1. Pi 2 is going to end up at 4 pi over 3 1. 2 pi 0 is going to end up at 7 pi over 3 and negative 1. Three pi negative 2 is going to end up at 10 pi over 3 and negative 3. And then lastly, 4 pi and 0 is going to end up at 13 pi over 3 and negative 1. I will connect the dots and I'll end up with this graph right here. You will notice that the graph has been moved 1 unit down, so that means the midline of this graph, right, where the graph was centered, is now going to be 1 unit down. But the properties are still the same. The center of the graph has moved 1 unit down. The entire graph has shifted pi over 3 units over, but the overall shape makes sense. I'll highlight this graph just so it's a little bit more visible to you. This is the graph that we're now looking at, the final graph. However, I want to make sure that my graph is fully complete in the domain of 0 to 4 pi, because that's the domain I'm working with. So you'll notice by shifting the graph over, I have now created a bit of gap at the front of that graph. I need to fill in that gap. I want to see what's going to happen to that graph in that gap. So between 0 and pi over 3, I'm going to extend that graph. If it kept on going, it's going to end up going down towards the bottom over here. Like that. Right? Would have done that to try and fill in the gap. And this final graph over here is now the graph of y equals 2 sine 1/2 x minus pi over 3 and then minus 1. Okay, that's what the graph is. So far so good? Right, transformation is all we're doing. We're doing our expansion compression together, and we're doing our translations together in one go, just like we did previously in previous units. Only difference is because these are sinusoidal functions, their scaling is a bit different, right? The way they're organized is a bit different. Are we okay with this? Okay, let's try one more example just to make sure you get the hang of this. First, predict how the graph of y equals 1/4 cosine 3 x plus pi over 6 plus 2 is going to be related to y equals cosine of theta. So look at that for a brief moment, write down what you think is happening, and then we'll compare our answers.